So we are in to the conservation of energy section. We're going to review that section really quick and then because we went through it yesterday, but then we'll review it again today, and then we'll go to the potential energy diagrams. We'll be looking at stability. And then tomorrow we will have class, since tomorrow we won't have class because you're going to be gone. We're having lab today, class today and lab today, class Friday. There we go. So class Friday, we'll answer questions and do homework problems. So what is conservation of energy? Conservation of energy is really just this realization that energy is never really lost except in extreme circumstances when it is turned into mass, which we're not talking about yet. And so we have all these different kinds of energy, like work and kinetic energy and gravitational potential energy and spring potential energy. And all of these things can trade back and forth. You can do work on a system to remove energy from a system by having work being done by friction, for example. If friction does work on a system, it removes the energy from the system because it will slow down the system in some way. It essentially takes kinetic energy out of the system. But you can also do work on a system by adding a force, and you could add energy to the system by if you do work with a force, you can increase the kinetic energy of a system. Or, yes, I am recording, thank you. And you can also increase the potential energy of a system by pushing something up a hill, gravitational potential energy, or by compressing a spring potential energy. You can also remove energy from a system by using work if you have an outside force that is not necessarily friction, but just pushing against something to slow it down. That can also be a force that takes energy out of a system. But the important thing is to identify your system. What is your system going to be? What is the thing you're trying to study? And it's a very good idea to keep this as simple as possible. For example, if you have two cars colliding together, then make your system the two cars. Don't include the earth. Don't include every little thing in between the cars or outside the cars. Just deal with the cars. So on and so forth, so they can trade things back and forth. We did this example. Also it's important, so in this section here we talk about the problem-solving strategy for conservation of energy. Important to define what your system is. It's important to identify all the forces acting on the bodies that are in the system, and then determine if those forces are conservative work or non-conservative work. Remember that conservative work is the kind of work that can be undone very easily. So if you lift something up a hill without friction, it can fall back down the hill without friction and nothing has changed. But if you lift something up a hill and there is friction, then some of the work that you do lifting it up the hill is work against friction, which turns in heat and gets lost. That is non-conservative work. Whenever friction is involved, essentially, it's non-conservative work. What you want to do is you want to be able to recognize which forces are going to be doing conservative work, which ones are going to be doing non-conservative work, and then you want to set up an equation, because the equation for energy and work looks like this, where you have the non-conservative work on one side of the equation. This is a better version. Non-conservative work on one side of the equation, and then essentially all the conservative things on the other side of the equation, like the change in kinetic energy, which comes from conservative work, change in potential energy from conservative work, and so on. And that way, all this conservative stuff happens, and then you subtract off this one to get it equal to 0, and then you're good to go. And then you're going to apply this conservation of energy equation, which you're going to put this all together You're going to figure out all the energies, and then you're going to put the non-conservative works on one side, all the changes in kinetic energy and the changes in potential energy on the other side, and solve the equation for something that you don't know, in essence. That's what you're trying to do in the end. So we did this with a simple pendulum, a pendulum that's being raised up to a particular height and then dropped, and it swings down to this lower height. Because you've raised it up to this height and there's going to be very little friction involved, we're going to say no friction, then that's conservative work that you did to lift that up there. When you let it go, it will gain back the energy that you put into it. You put in some work to change its potential energy. It's going to turn that potential energy into kinetic energy without any loss of energy. And so your equation is really quite simple. There's no non-conservative work. So it's initial kinetic energy, it's a final kinetic energy minus initial kinetic energy, final potential energy minus initial potential energy. And when you solve that equation, you get something like this, where you have just the initial potential energy on one side and just the final kinetic energy on the other side when you solve it. Then you can solve this for the velocity, and it ends up being the square root of 2gh. Then you just plug in numbers. Now, there's a little bit of work you have to do beyond that, because the height that you lift it, they don't tell you the height, they tell you the length of the string and they tell you the angle, so you have to do some trigonometry to figure out this height, and that's not that big a deal. But anyway, once you've got that done and you know the actual height that it's lifted, which turns out to be the length of the string minus the length of the string cosine theta, then you plug that into your formula and you get 1.62 meters per second of speed of the ball at the bottom of its swing, because this is the amount of velocity that is going to give you the correct kinetic energy for the amount of potential energy you gave it lifting it up to here. And that's conservative transfer. Now here's a different one where we're actually going to have some non-conservative work involved. We're dropping a big flat panel of stuff and it's got some air resistance. So there is some non-conservative work being done. We're going to use a different equation. The non-conservative work now is going to be equal to the change in kinetic energy plus the change in potential energy. Remember that change in kinetic energy and change in potential energy are defined thusly. Let me bring it up here. So this equation looks like this. Non-conservative work equals change in kinetic energy plus potential energy. This change here can be written separately. So change in kinetic plus change in potential. And if we write it all out, then, well, if we write it out in terms of kinetic final and initial, this change in kinetic energy is kinetic final minus kinetic initial plus potential final minus potential initial. Right? That's what that is, and that's equal to the non-conservative work. Now, if we write it out even further, there are different types of energies that we can put into these things. So far, we've only learned about one kind of kinetic energy, although there are different types of kinetic energy. The one type we've learned about is linear kinetic energy. So 1/2 mv final squared. And remember, in the book, they don't put the F for final, so we'll just leave that off. 1/2 mv squared minus 1/2 mv naught squared, which is our initial velocity, right? And potential energies, we actually have a few different kinds of potential energies. We'll put these in parentheses. We possibly could have some gravitational potential energy. So our mass times gravity, which is the weight, and we multiply by our final height. And then we subtract off our mass times gravity times our initial height. It could be a change in gravitational potential energy, but we might also have to add into that a change in spring potential energy. We've learned about spring potential energy. Spring potential energy is 1/2 times the spring constant K, little k. This is big K. Big K, little k, what begins with K? Okay. Times how much you stretch or compress the spring, which we usually call X, squared. And you would subtract off then the final potential energy, 1/2 K X naught squared. So you could have spring potential energy. And there are other types of potential energies. There's chemical potential energy that's stored in chemical bonds. You learn about that if you take a chemistry class. And there's vibrational kinetic energy, there's rotational kinetic energy, there's all kinds of kinetic energies. But they all kind of, every single one of those kinetic energies kind of, potential energies, I keep saying kinetic energies. There's different kinetic energies, which are vibrational and rotational, but there are also more different kinds of potential energies, mixing these two up. But all the potential energies are ways of storing energy that aren't technically movement within the system, and then the kinetic energies are movement energies. Anyway, point being, there are more, we're just using these ones so far. And that's why in the first example we had some kinetic energies, so we had these, we had some potential energies, we had these, but we didn't have any spring energies, so we didn't have these ones, and we also didn't have non-conservative work, so this non-conservative work over here was equal to 0, and we ended up with 0 equals, and at the beginning of that problem, we had potential energy, so we had some initial potential energy, that's this one right here. We had a minus mgh naught, but our final potential energy had an h of 0, so this one goes away. And then we had a final kinetic energy, but no initial potential energy, because a final kinetic energy, but no initial kinetic energy, because the initial velocity was 0. So we ended up with this equation, 1/2 mv squared minus mgh, and they ended up solving this by adding mgh to both sides, so they got mgh equals 1/2 mv squared. That's where that first equation came from. It's all from this equation. They wrote it down a little bit differently, but it's still the same thing. In this second problem, we actually have a panel that's dropping, and it has some wind resistance, some air resistance. So we do have some non-conservative work over here. We don't have an initial velocity because it's being dropped. Whenever you drop something, the initial velocity is 0. So we won't have an initial velocity, but we will definitely have a final velocity. And it's dropped from a height, some initial height, so we have an initial potential energy. And it comes down to a certain height, whatever that is, so we'll go ahead and consider that we have a final gravitational potential energy, even if it's 0. It's possible it could be 0. And we don't have any springs involved unless this panel hits a spring and compresses it at the bottom. Since it doesn't say that, then we don't have any spring potential energy. So our next equation is going to involve some potential energy, some kinetic energy, and some non-conservative work. And remember that non-conservative work is a force times a distance, right, in the direction that you're moving. So let's go back and see what this looks like. We have our non-conservative work, which is the energy done by, they're calling this energy dissipated, which is the energy done by the non-conservative work, right there. And that has to equal the change in kinetic energy plus U. Now, why do they put parentheses or absolute values around these? They're doing absolute values around these because keeping track of the sign on both sides of the equation is not always that easy. If you follow the rule that all energy into the system is positive and all energy out of the system is negative, then you can kind of keep track of it, but still a lot of people struggle with keeping track of it, so they're just going to take the absolute values. Initial kinetic energy at y1 is 1 kilometer. At y1 equals 1 kilometer is 0. So this y1 is, or yi rather, is our initial height. So we're going to use that as our h essentially. But our initial kinetic energy is going to be 0. It's going to be dropped, and it's not going to be moving right when we drop it. Right after we drop it, it'll start moving. But right as we drop it, it's not So the non-conservative work is set equal to the energies, and we're going to actually solve for the work. That's what they want us to solve for. They want us to know how much how much energy is dissipated, or how much work is being done by the air resistance. So we're going to take the difference in kinetic energies, and they tell us that the kinetic energy at the bottom of its fall, which is going to be at some height that they hopefully tell us, we're dropping it from 1 kilometer. Mass of the panel is 15 kilograms, hits the ground, so we're going to say that the ground is at 0 height since it's 1 kilometer above the ground. So the final height is 0 and it hits the ground at 45 meters per second. That's our final velocity. We've got everything we need to know. So here's our initial kinetic energy minus our final kinetic energy minus our initial kinetic energy. 45 meters per second minus 0 meters per second in these two formulas. And then our final potential energy, which is at the ground, which is 0, minus our initial potential energy at 1,000 meters, right? Plug in all our numbers, our masses, our velocities, and everything else, we get 130 kilojoules of energy total in the change in kinetic and the change in potential. And that is going to be equal to the amount of energy that was dissipated during that process. Now, why? A lot of students look at this and say, why is the change in kinetic plus the change in potential equal to the energy dissipated? Well, it's really quite simple. If this panel had no air resistance, what would happen in this equation? What would change in this equation if the panel had no air resistance? It's falling, and it starts falling at 0 speed and ends up at 45 meters per second speed. Is that going to change if there's no air resistance? Will the speed of the panel change? Absolutely. In fact, that's the only thing that's going to change if there's no air resistance. If there's no air resistance, this number is going to be bigger. It's going to be going a lot faster. So this whole number here is going to be bigger. This number is going to be bigger if there's no air resistance. The fact that there was air resistance changed this velocity, and that change in velocity comes from this thing over here. So this thing over here ends up equaling the difference here, right? So without air resistance, we plug in a different velocity there, and it's going to move a lot faster. So this is actually a very interesting thing that they do here. So here, what they're doing here is they're taking the kinetic energy here, setting it equal to the total energy minus the potential energy, because in reality, what this equation is up here, this one right here. There we go. In reality, this equation right here is equal to the total change in energy, which is what they have written right here. The total change in energy between 2 points is equal to the total change in kinetic plus total change in potential energies. So what they've done is they've taken that equation and they've solved it. They've essentially solved it at a particular point for the kinetic energy. Kinetic energy is 1/2 mv squared equals the total energy minus the potential. When you solve this, you get this thing. You get this v. You solve it for velocity, which is equal to the change in distance over change in time. That's just the definition of velocity, right? And that ends up equaling the square root of 2 times e minus ux over m, according to this equation. Well, that's interesting, I guess. But what they do with this is they actually are going to take a derivative of each side. They're going to multiply both sides by dx. They're going to invert it, and they're going to take a derivative. And they actually find out how to calculate the time, right? Essentially, what they're doing here is they're saying if you know the energy, you can figure out the time. And this is actually quite important for modern physics in particular. It was in modern physics. We're going when we take on we'll take on modern physics a little bit next semester, not too much in this class, but a little bit. But in modern physics, when we mean modern physics, we mean everything that happened after the papers that Einstein wrote in 1905. Literally, that's what it means. You ask any physicist in the world. Ask them what modern physics is, they say anything after Einstein wrote his papers in 1905. In 1905, when Einstein wrote his papers, he opened the world of quantum mechanics, he opened the world of relativity, he opened the world of all things that we consider modern physics with these 5 papers that he wrote. One of the things that included was the idea that particles have a behavior that is not necessarily set in stone. In other words, it can change randomly. Random behavior of particles. So it's like setting up 2 experiments exactly the same and getting different results. You have 2 experiments that are set up exactly the same. You have 100 experiments set up exactly the same, and they all come out slightly different. And it's not just because of error. Even if you had 0 error in the experiment, they would still come out different. And it comes out according to some laws of statistics. And so what they were able to show after Einstein wrote these papers and they started doing experiments on them, is they were able to show that nature actually behaves statistically. Nature, there's no such thing as you do this, you do A, you get B. In nature, you do A and you get some spread of possibilities around B. And it's a spread that is easily mapped out using statistics. It is very statistical behavior. And we shouldn't have been surprised by this. Every time we do science, we get statistical results. And we just assume that the most common result is the correct one. We've assumed that for thousands of years. But in reality, it's not true. In reality, even at a very, very microscopic level where you would expect very exact results, you always get a spread of results, and at that microscopic level, that spread is much more quantizable, much more quantized, I guess you should say. So anyway, the point is that they were able to show this, and they were having this argument at a conference one year. Whereas they have a picture of this conference on one of these posters, I can't remember. But anyway, they had this conference every year in Europe before Hitler took power in the 1930s. Is about when they stopped it. And all these great scientists would show up, people like Einstein and Madame Curie and Heisenberg and all these people. All these famous scientists would be there, and they'd argue and argue and argue about the different things in science. And one of the things that they argued about was this variability of results. And it was actually Heisenberg that was arguing that this was true, and Einstein was fighting against him. Einstein didn't believe it. Einstein didn't believe a lot of the results of his own experiments. He wanted to be able to prove them conclusively, and he struggled to do so. But Einstein was arguing and arguing and arguing, and Einstein said, wait, if what you're saying is true, then time and energy have to be related to each other. Well, again, he should have known that. This is something that was done hundreds of years before Einstein. So even Einstein wasn't perfect, but he was actually thinking of this when he said that, and then they actually went ahead and proved that it was true. So it's kind of interesting that time and energy are very related to each other. So are time and distance related to each other, to the point that many scientists believe that there's no difference between time and energy, and that there's no difference between time and distance. They're actually the same thing. Kind of strange, but it's true. So that's conservation of energy in a big nutshell. All right. So now we're going to talk about things that we call, we're going to talk about these potential energy diagrams. We often call these wells in physics because they tend to look like cross-sections of wells, like this right here. You have a bottom of the well and you have a top of the well kind of thing, right? Here you have 2 wells, and there's kind of this wall on either side and kind of a bump in the middle of the well. Why do we call these wells? Because they are kind of like energy wells. This is a representation of the potential energy in a spring with a mass on it. In this case, you have a mass in the middle and a spring on each side. So if it goes this way, it gets pushed back this way. If it goes this way, it gets pushed back this way. It works with just one spring. It doesn't have to have a spring on both sides. But it works with one spring too. But what does this mean? This means that if we go too far to the negative side, too far to this side, we increase our potential energy, right? If we go too far to this side, we increase our potential energy. And what does that increase in potential energy mean? It means that it wants to go back to lower energy, lower potential energy. Things that gain potential energy always want to get rid of that potential energy. That potential energy is not something that it's happy having too much of. And so if you see a diagram like this of potential energy versus position, you can actually tell where this thing is happy. Where is this thing going to be happiest? Right here. Right here, it has no forces on it. The forces are equal on it. It just sits still. It doesn't move. It's happy right there. You can also see if this thing has a stability to it. What I mean by stability is, will it continue doing the same thing, or is there a place where it could stop and kind of be in limbo or be in danger of doing something different? In this case, if you start this thing vibrating, it's just going to keep vibrating if there's no friction. It's just going to keep going back and forth and back and forth. If you sit it at the bottom here and you give it a kick, it goes up the hill and then it comes back down the hill, and if there's friction, it just eventually settles back down where it was. This is what we call stability. Stability literally means you give it a kick, it might move a little bit, but then eventually it just kind of settles back down to where it was. That's stability. Okay? We call that perturbation theory. To perturb something means to give it a kick or change it a little bit. And in perturbation theory, if you give it a little bit of change, like a little kick, and it goes back to where it was, that's stability. This is also called a stable equilibrium. The equilibrium point is where there is zero force. And this is called a stable equilibrium point because if you kick it to either side, it eventually settles back down in that spot. There is actually there's a mathematical, I don't think they give us the math, they kind of do down here. So that's fine. So here's another one. Here's a much more complex one. This one could literally be, well, this one could be like, this one would be like a glider here, like this glider on a hill. So it's at the top of a hill, but there's springs on either side. So you have these springs on either side, and then there's a hill in the middle that gives it a little potential energy in the middle. Is this right here an equilibrium point? If we put the car right here, will it stay right there? Sure. If we put the car right here, it is in equilibrium. The amount of force on this side, the amount of force on this side, or the amount of change in potential energy on either side is the same. Right? However, if you give it a little kick, is it going to go back there? Not necessarily, especially if there's friction. Right? And even if there's not friction, it's not going to. If you give it a kick and there's no friction, you give it a little force this way, it's going to slide down here, it's going to come back up here, and it's going to go past this point. Then it's going to come back up here and go over the top of this point. It's never going to come back to rest here if there's no friction, if you just give it a little kick. If there's friction and you give it a little kick, it'll come back up here and it'll come almost to this point, come almost to this point, and it'll settle down here. This is a stable equilibrium point. This is another stable equilibrium point. But this is what we call an unstable equilibrium point. So this particular well, or this particular potential well, has 3 equilibrium points, 2 of which are stable, 1 of which is non-stable. Now, how do we figure this out? How do we figure out where these things are at? If you've done calculus before, you will know. Have you guys learned about finding maximums and minimums in calculus yet? So you're right about there. That's right. So if you take the derivative of something, you find out how it's changing, right? If you take the second derivative of something, you find out where, no, you take the derivative of something, set it equal to 0, you find, and solve, you'll find out where it has a turning point, essentially, right? So that's where you find a maximum or minimum. If you take the second derivative and set it equal to 0, let's
That
see.
would be a possible inflection point. I don't think that's minimum and maximum to just set the first equal to 0.
No, if you take the second derivative and set it equal to 0,
That just
no,
be a concavity.
sorry, if you, yeah, that's what we're looking for. Yeah. So if you take the second derivative, set it equal to 0, and then plug in the point of the turning point or the maximum and minimum, then it will give you either a positive or a negative value or something like this. Yeah. So if you get to that point, then you'll know whether it's positive or negative, right? Then you'll know. Yep, that's correct. And that is if you are doing this in an energy position graph. It doesn't work for energy time or anything else. It's energy position graph. That's correct. And they actually do that here. So here they find the equilibrium point, and then they take the second derivative at the point, at x equals 0, so it's negative. So they're doing this, they find the equilibrium point here at 0, then they take the second derivative of this function. When they take the second derivative of it and plug in 0, they get a negative 4, and that means that it is, would you call that convex or whatever? It means that if it's negative, it's non-stable. It's not stable. Unstable. If it's positive, it would be the second derivative evaluated at x equals whatever this is, 1, 2, 3, 4, 5 is like 10, something, 8 maybe. If you evaluate it at 8, you'll actually get a positive number, which of course means that it's a stable equilibrium. So here they do something kind of interesting where they take that time equation we were dealing with before and they actually solve it in a particular, they actually integrate it. This integral is not something you can do just off the top of your head. You're going to have to either use a computer to do it or look it up in a table. They're using a computer to do it. They just search for it. How do you do this integral? Right? And when they do that, they get this very interesting result. They get the function x of t equals the square root of this thing, this constant, which is energy over the spring constant, and then the sine of the spring constant over the mass times time plus or minus this constant angle, 90 degrees. This is the solution for what we call a harmonic oscillator, something that we're going to deal with later in this book. So doing the math of the physics, essentially what they've done here is they've done some physics that created some math. They took that math and extended that math to the next step, which created new physics. It created a new formula or a new model for how things work. We already knew this, but we already knew this from experiment, but we've now proven it through theory. And this is what physics is all about, really. Usually you kind of have three camps in the physics world. And this is true in many sciences, but it's very, very true in physics. It's only slightly true in other sciences. But in physics, you will have some people that do nothing but the math side. And they never step foot into a laboratory. All they ever do is just work out the math and create models like this for other people to work with. They're called theoretical physicists, right? Then the largest group of physicists are the people that do a little bit of each, but mostly they mostly do experiments. So these are just what we call kind of like physicists or experimental physicists sometimes. But they're doing a lot of experiments, but they're also contributing to the theory. They're also doing some theory sometimes. They're working with theoreticians quite a lot, and they're doing lots of experiments. Then we have the kind of hardcore experimental physicists who don't want to have anything to do with the theory. They don't. All they want to do is look at the theory and to see if they're correct when they're done. They don't want to mess with it. They don't want to change it. They don't want to do anything else. And they're the pure kind of experimental physicists, and it's almost to the point that they're more like technicians and engineers, where they're trying to really make the technical side of the science exact. The vast majority of these people, though, are in the middle somewhere, but there are definite camps of the other two. So it's kind of an interesting way to go about science. And in fact, if you go on in physics or engineering, I don't know if they have a class like this in chemistry. They probably do. You wanted to do chemistry, right? You're looking into possibly chemistry. But anyway, I think they have a class like this in chemistry, but I've not been in graduate school in chemistry, so I don't know. But in graduate school, in physics and engineering, and probably chemistry, they have a class. In the case of physics, it was a 2-semester long, full-on 3-credit class, where all we did was look specifically at the mathematics in great depth of theory and great depth of application. We looked at the mathematics of advanced physics. Because here we're really looking at the results, but you really need to understand not only where it came from, but where it's gone. You need to kind of see the whole picture to be able to do the science very well. Mm-hmm. And so we spent 2 semesters just doing so much math. The textbook was like this thick, and we went through the whole thing and then some. I had notes I had hundreds of pages of notes, and it was a crazy class. Just one of these classes where everybody gets like half of the problems they do wrong. Everybody, even the teacher gets half of them wrong sometimes. And I remember taking one of the problems that we were doing to our teacher, and we couldn't do it. We'd spent an entire week on it, and none of us could do it. Like 8 people, we couldn't get it done. And we took it to him, and 2 days later, he brought it back to us, and he said, "Here's the solution," and kind of walked off. And we're looking through his solution. His solution was exactly the same as ours until he got to about halfway through where we got stuck. And he said, "At this point, you just have to assume this is true, assume this is true, assume this is true, assume this is true," which made it really easy. And then he finished the problem. And I'm like, "Are you kidding? You must be absolutely kidding. You're just going to assume all the hard stuff is not there." But, that's what it is. And he had good reasons for assuming those things. He justified them, but still it was driving us crazy. All right. So the last section of this chapter, and the last section of all these chapters for some reason, is sources of energy. I don't really think this belongs in a physics book, because this is more like geopolitics and engineering, but whatever. They're talking about all the different sources of energy, and then of course they're talking about, essentially what they're doing is they're trying to promote new kinds of energy other than the energies sources that are not very popular right now. Unfortunately, there's really only 2 energies on this entire thing here that are actually useful, believe it or not. Luckily, one of them is the biggest one, the fossil fuels. And there's a huge political debate about if fossil fuels are good or sustainable or whatever else. Well, frankly speaking, we've got about 1,000 years left on fossil fuels, and that's it. In 1,000 years, we'll be out. Well, you know what? 1,000 years ago, we didn't even know they existed. 1,000 years ago, we weren't even burning coal because we didn't know you could burn it. It was a rock. Why would you burn a rock, right? I think we're okay. And that accounts for all the increase in population, all the increase in usage. There is so much of it. Now, the other thing that is really, really popular for people to say is that it's so dirty and it's hurting our planet and it's scarring this earth and all these things. Show me where that's true. We can create energy from fossil fuels that is absolutely, completely pollutant free. We do it all the time. It does not. We're not required to create pollutants to use fossil fuels. We do because it's cheaper, but we're not required to. If we want to do it without it, we can. Why not just make that the rule? But we don't make that the rule. Why? Because that doesn't make anybody money. What makes people money is creating new ways that are expensive to make energy. If you think the energy companies aren't huge into this whole push for ending fossil fuels, think again. Because the energy companies are going to make 10 times as much money with solar than they ever would made with fossil fuel. They're going to make they've already made 10 times as much money just from the government alone, putting up these wind farms. Wind farms are like the least efficient way to get energy you could possibly imagine. The other thing that's efficient here, the other thing that we should be doing, that we have unlimited resources for and that is absolutely 100% clean and has killed fewer people, fewer animals, and fewer things on this earth than anything else, is nuclear power. Nuclear power is by far, statistically speaking, in every other way speaking, the safest and cleanest and most renewable energy source we have. We have an unlimited supply, literally unlimited supply of fuel. The fuel is absolutely recyclable. And this is how much of it we use. Look at this chart right here. That little pale pink sliver, that's nuclear. No, that's not it. This one's nuclear. Sorry, it's this orange one is nuclear. 2.7. I was looking at the wrong circle. 2.7% of the world's energy is nuclear. That is ridiculous. People say, well, what about nuclear bombs? You can't make a nuclear bomb with a nuclear power plant. It just can't be done. It's just not there. Not possible. What about meltdowns? We have had exactly one meltdown in the history of nuclear power plants. One. It was in Russia. It was in 1982, and it was a poor design of a power plant. And we figured out what to do to fix that. And people say, well, what about 3 Mile Island in Pennsylvania? 3 Mile Island was not a meltdown. 3 Mile Island was a failure of the power plant, which would have resulted in a meltdown had the safety features failed as well, but the safety features did not. There was a failure in the plant operation, which can happen, but the safety features kicked in perfectly, and there was absolutely no loss of anything, no radiation leakage, no anything else. But these things here, you would be appalled to find out, and the information is available if you want to research it. But you would be appalled on the amount of energy that has been literally given away to people to do these things and they never did it. Millions upon millions of dollars to individual companies. In total, billions, maybe even trillions of dollars over the past 30 years have been given to companies to do these things. And who gives it to them? Politicians. Why do they give it to them? Because they're buddies, right? This is one of the biggest. Energy is one of the biggest ways to give money away to people in politics of the past 50 years. It used to be military. The 50 years before the last 50 years, which was the Cold War era essentially, World War II on, the biggest thing was military. You got your money by having a company that made military satellites or military planes or military this. That was the way to give money away. And there were like 10 companies that did it. And now it's like a million companies. Every little startup company. If you would give money to a politician, then you start a startup company in solar, and you get millions back in grant money from them, and then you declare bankruptcy and walk away with the money. I mean, it's happened so many times. It's kind of ridiculous, and they're not even shy about it. I mean, we caught people doing it, and they never even got convicted. They're stealing money from the government, from us, and it's ridiculous. My favorite one is when the U.S. government gave away $500 million for a company to build an electric car for America. Want to know what company they gave it to? Saab. Saab is a company in Sweden. Why would they give $500 million to a company in Sweden when we have 4 of the biggest car companies in the world, 3 of the biggest car companies in the world, right here in the United States? Why would we give it to Sweden, to a car company that is super tiny, first of all, a car company that is completely renowned for their terrible cars? They make terrible cars, they can't sell them, they can't even make them, and a car company that since then has pretty much kind of gone out of business and taken that money and run it. $500 million. Not only that, but we had a car company here that had already made an electric car. We had 2 car companies here that had made an electric car. And Saab had never made one, and they still haven't made one, and they're never going to make one. $500 million they walked away with. Ridiculous. Politics and science are a bad mixture because these kinds of things happen. Unfortunately, they are an unholy necessity because nobody wants to pay for science, and so we have to go through the government and get it through tax money. That is changing somewhat. People are starting to pay for science more and more, but this huge complex of government officials and science industry officials trading favors and money is too strong to really end at this point. It's unfortunate, and I hope that as our new generations of scientists go up through the scientific ranks, they can figure out something to do to change that. It's not likely to happen, but who knows? Anything's possible. I can't figure out a way to fix it, but the only way I could possibly think to fix it is to fill Congress and the White House with scientists that actually have values. Like that's ever going to happen. The last scientist to run for office had a physics degree. He ran 8 years ago, and he didn't even make it out of the primaries. The last one to run for president. He was mocked because he had a physics degree. He's like, what could you possibly know about politics? What could you possibly know about running this country if you only have a physics degree? And he's like, really? You think politics is rocket science? Because it's just not. Anyway, it's not to say that these technologies have promise. Some of them really do in some situations. But I mean, people talk about solar as if it's solar as if it's going to really change something. You can't really use photovoltaic. So here's the photovoltaic, the one that everybody really thinks is valuable. 0.06, right? It's a very, very low possibility. We can only use it in some parts of the country, some parts of the world that have sun all the time. And at night, of course, they don't have sun, so what do you do at night? Well, you have to charge batteries, expensive, or you have to have a big lake way up in the mountains that you pump water up to all day and let the water come down and turn turbines all night. It's only two real possibilities for it. It's not really that efficient, considering that you have to store the energy somehow at night for use at night. Anyway, that takes us to the end of Chapter 8. Is this Chapter 8? Yeah. So what we'll do on today we'll have our lab, right? Tomorrow we won't have class or lab. So tomorrow I get the day off. Sweet. What's that? Oh yeah, Tommaso could have class because he's missing class today. Right? Okay. Never mind, I'll have class tomorrow at 11. Don't get the day off. I never get the day off. My kids get the day off all the time. Packers got the day off. Why don't I get the day off? And then Friday we'll answer any questions out of the homework, so make sure that you get started on the homework so that you have questions. Best thing in the world to do is to start on every problem until you get stuck, and then come in and ask your questions. And then we can finish all those problems. We will see you on Friday. So you guys are starting at 11 for the lab today?